I'm very pleased to have Jeff here. We are planning this for at least in the last 2-3 months.
Yeah.
And we are very happy to have you here. And so Jeff is very well known, and saying things about him is not really easy. You go to his website, you see tons of resources and things that are really encouraging and nice to see, from videos, from books, from papers. So name any prize in Canada, you get to see Jeff has received it. So a public figure, he wrote books that are not mathematical. It's just other types of books that are published 13 times, bestseller in Canada at a point, right? And so I can tell you the prizes that he has received in 2006, CRM SSE prize, and also COPS in 2007, SSC gold medal in 2013, fellow of Royal Society of Canada, fellow of IMS, and he's a great teacher. I was not lucky to take his courses when I was a student. Jeff came to University of Toronto. When I was in second year, I already passed all the courses, so I was just doing my research, not lucky to get his probability courses. And the book is called Struck by Lightning, 16 times published and in 10 languages. That's what I copied from his own website. 16,000 citation in Google Scholar. You name it, there's so many things I can say about Jeff, but I don't want to bother him with too much about things that everybody almost know. So his main work is on MCMC, Metropolis, but algorithm has, I've seen a similar talk from Jeff long time ago. I'm sure these are some stuff that's more perhaps recent. Anyway, this is a public talk, and I'm sure he's adjusting it to public, basically audience. I really appreciate that. Yeah, I don't want to say anything more. Thank you.
Thank you. Great. Okay. Thank you very much, Mahmoud, for that very nice introduction. And thank you to everyone for being here and being such generous hosts at the University of Ottawa. And thanks to Kenzie and the National Organization for arranging all this. So it's nice to be with you today. Et pour commencer avec quelques mots en français, je peux vous dire, je sais que je suis en université bilingue et c'est une émission pour tous les Canadiens qui est bilingue. Alors, si vous voulez, vous pouvez me poser des questions en français aussi. But I'll do this in English. And so as I get older, I find that instead of giving talks about my latest paper, I tend to take more of a bigger view of what have I been doing over the years. And I think you could summarize my research in a sentence. You'd say I've tried to speed up the Metropolis algorithm by using mathematical theorems. So maybe when I die on my tombstone, they can say, here lies Jeff Rosenthal. He tried to speed up Metropolis using theorems. And that would be the story of my life. So I'm going to start at kind of the basics here, because I know people might be coming from different backgrounds. And so hopefully this will work, and hopefully we can all see the screen and everything with the Zoom and all those things going on. So the basic motivation for most of sort of Markov-chain Monte Carlo algorithms and so on is that we have some probability distribution that we're interested in. So I'll think for this talk, we'll have a density function pi. Hope you can see that. I'll usually write in blue. And we say that's a density function that we're interested in. And most common in my world, that comes from a Bayesian posterior distribution. But it could really be any probability distribution that you're really interested in for some reason in some particular problem. And you want to be able to compute things about it. And you can think of it as wanting to compute expected value. So you want to say, hey, what's the expected value with respect to this density pi of some function h? And h might be the indicator function of some event. So maybe it's a complicated Bayesian posterior model from maybe some medical experiment, and you want to know, did the blood pressure go up or down or whatever? And you say, well, we have some complicated Bayesian posterior pi depending on all our patients and models and all these things. And then maybe h is the indicator function, whether the blood pressure went up by more than a certain amount. And we say, hey, we'd like to know that probability. We'd like to compute an expected value like this. So that's kind of the motivation. And of course, we all know how to do integrals. We did it in first year calculus. So if you have a simple function, you can just integrate it. But if pi is very complicated, maybe you can't use calculus. But then you say, well, you could still use numerical integration. That works well in small dimensions. But as you get to higher dimensions, more than about 6 or so, it's hard to do numerical integration. And then you say, well, we've got this big complicated thing. It's really some sort of an expected value. We'd like to compute it. Maybe we can't use simple calculus. Maybe we can't use numerical integration. So we do what I'm sure you all are very familiar with, of some sort of a Monte Carlo algorithm, that is, get random samples. And if we could have a bunch of IID random samples, x1, x2, x3, and so on, which maybe there are high dimensional vectors on some space, depending on all the different variables of your complicated model. But we say, well, if we could make the computer sample all these different things, then we could just take averages and we can say, we have the right samples. So therefore, if you want to know an expected value of some function h, you say, well, no problem, we'll just take the average over these samples. Or if it was a probability, say, hey, what fraction of these samples had that probability? And that would give us our answer. So that's Monte Carlo algorithms in a nutshell that probably you all know. And then Markov chain Monte Carlo, or MCMC, and in particular the Metropolis algorithm, says, well, maybe you can't even get your computer to write a computer program that will give you this sequence of vectors with all the right probabilities. If you could just do that, you could average it, but maybe you can't. But maybe instead you can do an iterative procedure. And the original MCMC is the Metropolis algorithm, which goes back to 1953, which always blows my mind when you think what kind of computers they were working with, right? We're so spoiled today with our computers, but they had big, complicated computers, took up whole rooms, and yet they ran the Metropolis algorithm. And I'll state it as follows. I'll say that we have a proposal distribution, which I'll think of as being symmetric and usually a normal distribution. And you start with some initial vector x. So maybe you've got, high dimensional, maybe it's 100 dimensions. So x0 might be just some 100-dimensional vector that you start with. And then you just iteratively update it. So given the vector at time n-1, it's just two simple steps. The first is you propose a new step. So for example, you might propose a new state yn, maybe from this, say, normal. So I might say it's normal centered at the old xn-1 with some covariance matrix. You propose, you say, hey, maybe this is our new vector. And then you either accept that new vector or you reject it. Okay, so it's probably most, the Metropolis algorithm, but it says we make this new vector, and then we say, well, maybe I'll choose that new one, or maybe I'll stick with the old one. And the simple rule is you look at the simple thing, you look at the ratio of your target density pi, right? That posterior, that thing you really want to know all about pi. You look at pi at the new vector over pi at the old vector, and look at that ratio. And if it's more than one, you always accept the new proposal. If it's less than one, you accept it with that probability. So in other words, this is an iterative process. You start with some x0, then you make an x1 by this simple process, then you make an x2, you make an x3, and so on. And this is a Markov chain. And what's it good for? Well, I'll try to convince you what it's good for and what kind of theory we can do. And I'm going to start off, I'm going to go a few times to a simulation that I wrote here, a little simple simulation. So hopefully you can all see that. And what do I have here? Well, on the bottom, I don't know if you can read the numbers, but there's 6 points, 1, 2, 3, 4, 5, 6. And this stands for our state space, which usually would be maybe a 100-dimensional continuous state space. But for us, let's just make it be 6 points. And you have these blue bars, which are the density pi, which normally could be a density in a big complicated space. But now it's just things that add up to 1. So it looks like the first one's about 0.2, and then 0.1, and 0.25 or something. So anyway, these things add up to 1. And these are 6 different probabilities. And then most importantly, at the bottom, we have this black dot. Can you see my mouse there? Yeah, so this black dot is our Markov chain. So it's going to run a Metropolis algorithm, and it just happened to start at the state 2. And it's going to proceed by proposing a new state and then accepting or rejecting it. And the way I programmed it is when it proposes a new state, it's going to, with equal probability, propose to add 1 or subtract 1 to the current state. So often this would be from a normal distribution, but let's just say we add or subtract 1. And then what it does is it randomly chooses one of those. So in this case, it chose this. So it's proposing to move from 2 to 3. And then once it does, it has to decide whether to accept or reject. So yellow means it hasn't decided yet. And then remember, the rule is you look at pi of the new state, which is pi of 3, which is this side here, divided by pi of 2, this state here. And this one's bigger, so you're always going to accept it. So I know if I do one more step, it's going to turn green, which means it accepts it, and it means the Markov chain moves over to 3. Okay. And then it does it again. Now it's at 3. It proposes either to add or subtract 1 randomly. Okay, it chose to subtract 1. So it proposed to move back to 2. Now we look at pi of this state, which is about 0.1, over pi of this, which is about 0.22, I think. So it's a little less than 50% chance, I think, that it's going to accept it. And oh, it turned green. That means it did accept it. So it goes back again. And it does this again. Maybe I'll get this running continuously. So at that time it proposed to move to 1. It's going to accept it. And now it's going to decide okay, it rejected there. So finally it rejected. That means it stays at 1 and it tries again. If it proposes 0, it always rejects because pi is 0 there. 2, it might, it rejected again. So it's getting stuck at at 1 for a little while, but hopefully it won't be forever. I'll speed that up a little bit more. And as it starts going, okay, it accepted to go to 2, and now it's moving on. Let me speed it up a little bit more. And each time it's going to, oh shoot, you know what? I pressed the wrong button. I didn't mean to increase the radius yet. I meant to speed it up. So sorry, leave it the way it is. And it's proposing. So again, it's proposing and then it's accepting or rejecting each time, okay? So that's the Metropolis algorithm in a nutshell. And then while it's running, I want to add one more thing, which is the empirical distribution. Let me just see a second, there we go. So the empirical distribution, what's that? I put in some black bars now. And these black bars are just keeping track of what fraction of the time it's spent at each of these states so far, okay? So it hasn't made it to 5 or 6 at all. Spent a lot of time at 1 and 3 and quite a bit of time at 2, a little bit of time at 4. And if we run this, I'll get it going faster if I click on the right thing this time. So let's do a faster Markov chain. It's proposing, it's accepting, it's rejecting. Well, it's not doing great. It hasn't made it to 5 or 6 at all. There it is, finally made it to 5. And as it moves around, it's following this simple rule, right? Propose a new state, either accept it or reject it. And what's the point of all this? Seems like a bit of a mess, but what's going to happen over time? Well, you might be able to see the black bars will converge to the blue bars, right? That is to say the fraction of time that this Markov chain spends at all these different points will converge to the blue bar, which was the target, right? That was our big important posterior distribution that we really want to know about. And why is that so exciting? Well, because the blue bars are what we really wanted to know, right? It's this big, complicated, high-dimensional thing. We wish we could compute expected values and probabilities and so on. The black bars, that's just keeping track of what's happened on our computer, so that's easy. So the point is, if we can use the black bars to estimate an expected value, maybe that's a pretty good estimate from the blue bar. So, okay, so I will come back to this sample, this simulation, but let me go back to the slides now. And so that's the Metropolis algorithm in a nutshell. So at least if you follow me so far and you didn't know it, now you know the Metropolis algorithm. So I'll just say I'll have a few asides in green. And one of them is that today I'll stick to the symmetric Metropolis algorithm. You can also do asymmetric versions where the proposal, instead of being just 50-50 or just a normal distribution, can actually use things like the gradient to try to push you in the right direction. And we do have some other results about that, including something called the Longevat algorithm, which follows a differential equation. But I won't focus on that today. I just wanted to mention it. So, okay, so then you say, well, we've got this algorithm, right? This Metropolis algorithm, it proposes new states, it accepts or rejects. And I told you that the black bars would converge to the blue bars. I don't know if you believe me or not, but you shouldn't believe me unless I have a proof. But fortunately, there is a proof of that. So this goes back to 1953, and they said that it would converge. And I'll mention just why it's true, because it's going to be relevant to what I say later. And this is probably, if you've ever taken a stochastic processes course, you know, Markov chain convergence theorem, right? And it says if you have a Markov chain, well, this Metropolis algorithm, that acceptance probability, that minimum of 1 and pi of y over pi of x, was chosen just right to make the process reversible with respect to pi. So that is, it's the same probability of, if like pi of x, the probability of starting at x, times p of xy, the probability of jumping from x to y, versus pi of y times pyx. So it's just the right acceptance probability, and that guarantees that pi is a stationary distribution, if you remember your Markov chains. And once you have a stationary distribution, then as long as you're irreducible and aperiodic, which you almost always will be in MCMC, so let's not worry about that, then it will converge. So in other words, basic Markov chain theory that goes back, what, almost 100 years, tells us that this is going to converge. So it means that for large enough n, this is approximately in the distribution pi. And if you do things like estimating, so if you estimate an expected value, we really wanted to take an official, expected value with respect to pi, but that was too complicated. But if we just average up some values of h over an average of the sample, that'll be pretty good. I stuck in a little b here, if you can see, which is to say, we usually have what we call the burn-in, which is we don't count the first samples because they're not from a very good distribution, but throw some away, and then after a while count some samples, and they'll be approximately the right distribution. The black bars will be close to the blue bars, so we can average over those black bars. So that is the Metropolis algorithm, and probably you all know it's very popular. It's used in Bayesian inference. It's completely changed Bayesian inference, but it's also used in sciences and finance, engineering, all sorts of places that people are using MCMC algorithms. So that's the Metropolis algorithm, and that's MCMC. And then you say, well, what happens to somebody like me? I work on the theory side of things. So what can we say on the theory side, aside from just that it will eventually converge? And one thing you can talk about is optimality, or sort of optimal choice. And let me go back to the simulation. And let's see, let me zero the count. And let me get this running again. And so we already said we know how this works. You do plus or minus. It's not off to a good start, actually. But Let me speed it up a little more so we can get going. But while it's doing this thing and proposing plus or minus one, you might say, well, maybe that's a bit boring, just proposing plus or minus one. I'll slow it down a little more. What if instead I did plus or minus one or two? That is, each time with probability a quarter, it proposes to add one or add two or subtract one or subtract two, and then still have the same rule for accept reject. It says, well, you propose a new claim, then look at pi of y over pi of x. If it's more than one, you always accept. Otherwise, you just accept with that ratio. And you could run that for a while, right? And you can say, hey, I'm doing this. And the same markup chain argument would still work. It would still converge to the right thing. Pretty good. So is it better or is it worse? Well, why stop at two, right? I could do, say, plus or minus one, two, or three, right? Now it's saying, hey, so I'm going to propose to add or subtract one, two, or three with probability 1/6 each. And then I'll still have that same rule for accept, reject. It's still true that the markup chain theory works, that asymptotically the black bars will converge to the blue bars. Well, why stop there? Plus or minus 1, 2, 3, 4. And you might think, well, maybe it's better because we're proposing bigger, we get to take bigger moves. But you might think you don't want to go too far. Well, let me be a little extreme. Suppose I go up to plus or minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's not that great because it's usually going to propose things which are so far away that pi is 0, or in general might be very small, and it's not going to accept. So that doesn't seem so good. But if we just propose plus or minus 1 at the other extreme, well, that doesn't seem so good because each time it's not moving that far, right? It takes a long time to make its way over from one side to the other. So maybe there's some optimality there. And so right away, we can say, well, if you're looking at the theory, you could talk about how do we optimize? How do we make this Metropolis algorithm work efficiently? And what do we mean? We really just mean we want the black bars to converge to the blue bars as quickly as possible. So if you're with me on that, then we say, okay, well, how can we use an optimal choice? Well, so let's remember something else from your stochastic processes class, which is how if you start with, on the left-hand side, we just have simple random walk. That is something that you just add or subtract one each time with probability a half each. But then you start shrinking it down. So instead of doing it at time 0, 1, 2, 3, and so on, do it at time 1 over d, 2 over d, 3 over d, where d is a large number. So we're taking faster and faster steps, but also shrink down space. So instead of adding or subtracting 1, you just add or subtract 1 over square root of d. Then, as I'm sure you know, as d goes to infinity, this actually converges to Brownian motion, right? This sort of has this diffusive behavior, and that's what it looks like in the limit. What does that have to do with the Metropolis algorithm? Well, there's theory that's going back a while now. I guess I'm getting older, so things are longer ago. But it says, under some very strong conditions on pi, when they proved it, they said, if you do the Metropolis algorithm, but you first of all, let's speed it up by a factor of d, just like in the Brownian motion case. And then second of all, let's do it where the proposal, so it's a normal, but let's let the covariance shrink down by 1 over d. So you're essentially proposing steps of order 1 over square root of d. So just like for Brownian motion, go faster and faster, order d, but make smaller and smaller steps of order 1 over root d. Then if you look at, say, the first coordinate of your Metropolis algorithm in dimension d, under these strong assumptions, it will converge to a diffusion process. And in particular, it'll be what's called a Langevin diffusion, which means it'll still have the right stationary distribution, but it'll be this sort of continuous limit. And there's a number of things you can learn from that, but the most important, I think, is that there's a relationship between the speed of this limiting diffusion, so it's sort of how quickly it's moving around, how quickly it's mixing, and the acceptance rate. So A here is the average or the asymptotic acceptance rate. That is just what fraction of those proposals were accepted instead of rejected. And it says, you know what, there's a relationship that the speed is proportional to A times phi inverse A over 2 squared, and phi inverse, this is just the CDF of a standard normal. So it's saying there's some complicated function of the acceptance rate, which tells you the relative speed or relative efficiency of your algorithm. And if you graph it, well, you can see it looks kind of like this, where this is the acceptance rate, and this is that relative efficiency. So this function here. And you can see that it's small if A is really small, but it's also small if A is really big. So you have to stop and think about that. Well, if A is really big, let's say, well, what does that mean? That means you're accepting most of your moves. That sounds really good. But how can you be accepting most of your moves? It must be you're making very small moves, right? So that's like plus or minus 1. Whereas on this end, if acceptance rate is very low, that means you're rejecting most of your moves, which means you're proposing really, really big moves. That's like plus or minus 10. That's not so good either. So it says there's an optimal somewhere in the middle. And in fact, the optimal turns out numerically to be at about 0.234 or about a quarter. So what does this say? It says if you're running the Metropolis algorithm, as you run it, in addition to keeping track of the black bars and all that, keep track of what fraction of those proposals were accepted. And if it's about a quarter, then you've got a pretty good Markov chain running pretty well. If it's much bigger, maybe your proposals were too small. If it's much smaller, your proposals were too big. So this is sort of one of the very useful facts about MCMC theory. It says how to improve this Metropolis algorithm. It also, as a side point, it says that the sort of computational complexity is order D, because we had to speed up time by a factor of D to get these limits, and then we get these order 1 limits. But the main thing, if you want to focus on it, is to say there's a relationship between acceptance rate and efficiency. So that's something I'll focus on. So, and you can do the similar thing for those Langevin algorithms I mentioned. It turned out you get a different optimal scaling, 0.574, and a better computational complexity order D to the 1/3. Okay, so let me just present a few simulations about that, and then we'll think about that and see how we can modify it. So here is a 20-dimensional Metropolis algorithm that I simulated, and just looking at the first coordinate. And as a first try, let's say you're going to do a Metropolis algorithm where the proposal will be a normal distribution centered at the current point as usual, and let's say with just the identity covariance. So I say, okay, sure, let's look at the identity covariance. And I did 2 graphs here, so hopefully this will be clear enough. The left one is showing the target distribution is the blue. And then as time goes up, this is the way our Markov chain moves. So our Markov chain moved around a little bit as it went up. The right is just an associated histogram. So you can think of that as like the black bars from my simulation, and the curve is like the blue bars. And we want the black bars to converge to the blue bars. Well, they don't look like they converge very well here. And if you look at the simulation, you say, yeah, it's not very good. It started here, and it really didn't get around very much. And if you look really closely, and I don't know how well you'll be able to see this, you can get some hints. You can see that this was for 2,000 iterations, so a fairly long time. And you can see there's some fairly long times, like here, for example, where it's just a vertical line. And remember, time's going up. So what does that mean? That means it stayed in exactly the same place for a long time, which means it rejected those proposals, right? It proposed to move, but then it rejected. And you say, well, let's look at that rejection rate. And sure enough, you get the acceptance rate is just about 0.017. So very small fraction of the time did it accept those proposals. Most of the time it rejected them. So not very good. And you say, well, okay, we have some theory, right? It says, hey, that means sigma, this proposal covariance was too big, right? So, okay, no problem. Let's do it again. This time I used a really small one, just 0.001 times the identity in 20 dimensions. Not very good, right? So here we started here. We just wiggle around. We didn't move very much. Again, the black bars did not converge to the blue bars. And what's the problem here? Well, if you look closely here, there's no longer any patches where it stayed exactly vertical, right? Because it wasn't that it was rejecting everything, but it just wiggled just a tiny bit. It didn't move very much. And you say, okay, so maybe we didn't propose enough. And sure enough, now if you look at the acceptance rate, it's about 0.652, which is bigger than theory says. You say, okay, we were proposing things that were too small. So sure, it was accepting a lot of them, but it really wasn't moving very well. Third try. This time I played around a bit with the constant. I said, let's let the proposal be 0.02 times the identity matrix. And if we look at that, I played around with it enough that I got an acceptance rate pretty darn close to 0.234, which the theory said was optimal. Still not very good, right? This is where you get a little frustrated. You say, wait a minute, these black bars are still not converging efficiently to these blue bars. That's not very good. What's going on here? Well, basically it says there must be more to the story than just this one-dimensional parameter of how big the proposal should be. And so another theorem says, well, you can look at, if you run a Metropolis algorithm, you make these proposals, then you accept or reject them. Then if you know the proposal covariance, and you also know the target covariance. So here, so this is sigma sub pi is the target covariance. That is the overall covariance structure of that thing that you really wanted to converge. And this regular sigma, that's just the proposal covariance. And this is a little bit of a mess here, but it says, take the product of your proposal covariance times the target, take the inverse, take the square root of that times the inverse square root of that, and look at those eigenvalues, and you get some crazy factor here, which theory is telling us this is how much the Markov chain is slowed down compared to the optimal one. And you don't have to try to take that whole formula in, but I'll just say here that this is minimized, that is the slowdown factor is minimized when your proposal covariance is proportional to your target covariance. So what it means if you do a fourth try, where this time we choose the optimal, according to theory, covariance matrix, which is, again, some constant that I adjusted to make the acceptance rate be 0.234, but some constant times the target covariance. Well, that works pretty good. So this is still not perfect, of course, but now the Markov chain does nicely move around, explore the whole space. And if you look at the histogram, it's not perfect, but you say, okay, the black bars are kind of converging to the blue bars. So what's the point of all this? It says that theory does have something important to tell us about how to make the Metropolis algorithm work well, but it's not enough just to look at the acceptance rate. You better look at this other factor, which is sort of the shape. It's like when you do your proposal in high dimensions, it should be actually proportional to the target covariance. So that's sort of optimal scaling theory. And I want to switch topics now, but I'll just say that a lot of people have worked on that. We want to see how can we make use of it, but I'll just put as a quick aside that there's been a lot of extension of this to weaken the assumptions, to use it on targets which, let's say, are discontinuous, different types of multiple tri and Hamiltonian Markov chains, simulated in parallel tempering, pseudo-marginal MCMC. So a lot of you will know these things, block IID targets. So a lot of people have worked on a lot of different extensions of this basic idea of how to do optimal scaling, right? How to optimize the Metropolis algorithm with a good proposal that works well with the target and gives you good acceptance rates and good proposals, lets the black bars converge. So there's a lot one could say about that. It's an active area of research, but how useful is it all, right? So especially if you're more on the practical side, you might say, yeah, I want to use this Metropolis algorithm. I really want it to work well. There's crazy theory people, they come up with some theorems about how to optimize it, but can I really make use of it? And that's where things can get a little bit uncomfortable, right? So you say, hey, how can we use this? And suppose I say, hey, I want to run my MCMC. I really want to use this theory. It says, well, we want to get the acceptance rate to be about 0.234. That's pretty good. But also maybe we want the proposal covariance to be proportional to the target covariance. Well, that's great, but we might not know how. So I say, hey, I wish you could make the acceptance rate 0.234. Say, great, how do I do that? And I say, hey, you should make your proposal covariance proportional to the target. Yeah, but we don't know the target covariance, right? That was this big complicated density function that we were hoping to sample from, but we don't know how. And so what do we do? And as far as just the acceptance rate, well, that you can kind of do by trial and error, right? Because you say, look, it's too big. I mean, I did that really in the 20-dimensional sample. I said, look, it's too big. Let's make it smaller. Look, it's too small. Let's make it bigger. So you could do that with trial and error. As far as the shape of the proposals, you can't. That's a D by D matrix, right? And how can you optimize that, just using trial and error? So what can we do? And it's difficult to do in high dimensions. So instead, what we can do is maybe let the computer help us decide. And this gets into sort of the second part of the talk, which is to say, we have this optimality information. We wish we could use it, but we don't necessarily know how. Maybe the computer can help us figure it out, right? I sometimes say, computers are getting faster and faster. Human speed is staying kind of the same, right? So let's let the computer help us as much as it can. And so to set it up more formally, suppose we have a family of possible Markov chains. So I'll write it as P sub gamma, and that'll correspond in the simulation. Maybe I'll go back to this idea that we can, we could do plus or minus 1 or plus or minus 2 or plus or minus 3 and so on. So that'd be a whole family of possible different proposals, right? So we say, okay, we've got a whole family of possible different proposals. They each have the right stationary distribution, right? They're each valid MCMC that will converge if we run it forever, but we don't know which one's going to be more efficient. And suppose we say we're going to make a rule where at the nth iteration, we use one of these Markov chains, okay? So we use, I'll call it P sub capital gamma n, meaning gamma n's chosen according to some rules, some adaptive rules that maybe learned based on what we've learned so far, what we've updated. And we say, okay, we're going to use these adaptive rules, and that's going to choose it for us. So let me go back to the simulation yet again. And I'm going to now turn on an adaptive version. Maybe I'll zero the count again. And how's this adaptive version going to work? Well, the first time it's going to propose plus or minus 1 as usual, and then it's going to either accept or reject. But now the computer says, I'm going to update the Markov chain rules too. And in particular, the rule I put in, a simple little rule, I said, well, whenever you accept a proposal, that means maybe it's pretty easy to, maybe it's easy to accept. Maybe we can be a little more ambitious. Maybe we can increase gamma. So the second time, I'm not changing gamma, but automatically the computer is going to do plus or minus 1 or 2 now. And now it's going to propose, let's see if it accepts. Oh, it accepted that too. It says, hey, this is easy. Let's go to plus or minus 1, 2, 3. Okay, accepted that again. It's going to go to plus or minus 1, 2, 3, 4. It's getting a little big, but hopefully at some point, okay, now it did a proposal that was too big, right? And the rule is when it proposes something that rejects, then it says, okay, maybe I'm getting a little too big. Let me go back to, I'll get that running, to plus or minus 1, 2, 3. Oh, it accepted that. Now it goes to plus or minus 1, 2, 3, 4. Okay, rejected that. It's getting a little too big. Now it goes back to plus or minus 1, 2, 3, right? So get that going a little faster. So the point is, I don't know why it's highlighting. Oops. But anyway, so you can see as it goes now, it's not only running the Metropolis algorithm where it proposes a new state and then accepts or rejects it and moves on, but it's also tweaking the Markov chain as it goes. And in particular, it's tweaking it to say, I'm going to, based on if I've accepted the previous one, then I can make gamma a little bigger. If I've rejected, maybe I'm getting a little too big, I'll make gamma smaller. Unless gamma was already 1, it never takes gamma below 1. So this would be an adaptive version. And at first it seems pretty good because now we didn't have to figure out what's the best choice of this plus or minus. Is it 3? Is it 4? Is it what? What's our best choice? Well, the computer will just tweak it as we go. And especially on a high dimensional example where you can't visualize it like this, we can still figure the computer is tweaking it as it goes. But is that really such a good thing? So that's what I want to talk about for the rest of the talk. So let's say, can this help us find better Markov chains? I think the answer is yes. And I'll convince you that by using adaptation, we can find, the computer can help us find better versions of the Metropolis algorithm. But then you say, wait a minute, the whole reason MCMC works is because of Markov chain theory, right? And Markov chain theory says you have a Markov chain with the right stationary distribution and irreducible and so on, it's going to converge. Well, if we're tweaking the Markov chain as we go based on the past history, it's not a Markov chain anymore, right? So the one thing you can't do with the Markov chain is change it based on the past history, right? So if we're tweaking as we go, we're cheating. So all that Markov chain theory goes away. And will it still converge to pi? Sometimes. That is, it won't necessarily converge to pi. And that's where things get a little bit harrowing. So let's look at that a little bit. So let's look at the 20-dimensional example. And this is similar to what we did before, but this one I ran it longer and I ran an adaptive version. And this time I set up the adaptation now to say, well, we already have this theory that it's optimal if, remember, the proposal covariance is proportional to the target covariance. But we don't know the target covariance. But as we run the Markov chain, we learn something, right? We get some samples that are kind of sort of from the target, and we can take the empirical covariance. And then we maybe get some more samples and we learn some more. So we set up a sort of adaptive Metropolis, as people call it. And it says, well, start with just any old proposal covariance, run your Metropolis algorithm for a bit, look at the samples you get. And remember, these could be high dimensional vectors, compute their empirical covariance, and then use that to get you a better Markov chain next time. And run that some more, learn some more samples, then use the new empirical to get better. So it's sort of a chicken and egg thing where you're saying, if we knew what the target covariance was, then we could run a really good Markov chain. And if we ran a really good Markov chain, then we could learn what the target covariance is. But it's a chicken and egg. So as you go, so this is again with time going up. And this is sort of, at first it looks like just an ugly blob, but if you look at it more, sort of a fascinating plot, because at the beginning, as time's going up, it's running a bad Markov chain. And this is a bad Markov chain that's really not doing a good job of sampling from the overall target curve here. So it's bad Markov chain, but then it learns a little bit, right? It gets some samples from the target, says we can learn a little bit about the covariance. Now we run a little bit better Markov chain, and this is a better Markov chain. And now it gets new samples, which are a little bit better quality, and it learns more as it goes. And by the time it gets to about 1,000 here in the middle, this is actually a really good Markov chain, okay? So this is adaptive MCMC in a nutshell. Start with a bad Markov chain, learn as you go, tweak the Markov chain rules as you go, and eventually maybe you'll find yourself with a really good Markov chain. And so if you do a histogram based just on the second half, that is the part above this yellow line from the good Markov chain, now the black bars do converge to the blue bars, okay? So this is adaptive MCMC in a nutshell. It says, you know what? You can start with a bad Markov chain, learn as you go, get the computer to adapt as you go. So that is 20 dimensions. Just show you quickly it works, and you can do it for various other types of MCMC, which I won't get into. And seems pretty good. And what about higher dimensions? So here's a 100-dimensional example, looking at just the first coordinate again. Very similar, starts with bad Markov chain, gradually learns. And from about here, this is good Markov chain. So, and it takes about 300,000 iterations here in 100 dimensions. But again, the computer does that, right? I don't do anything. I just relax while the computer runs iterations, gradually figures out where's a way to run a good Markov chain. For this example, since it was a toy example where we knew the target, we could also compute that slowdown factor that I mentioned, which is how much worse it is than the optimal. And you can see what happens. It starts is really bad. It's hundreds of times worse than an optimal Metropolis. Here it's still 60 or 70 times worse. But oops, now it's actually getting very close to 1. And this means close to 1 means optimal. So we sort of, the computer, by adapting as it goes, manages to get to the point where it's running an optimal optimal Metropolis algorithm. Here's a 200-dimensional example, still the same, bad, learns as it goes, becomes good. And this one takes about 1 million iterations before you get a really good Markov chain going, okay? So I think it's great to say, it's good to say that it can help you find good things, and you'd never in 200 dimensions be able to tweak a 200 by 200 covariance matrix to get a good optimal proposal distribution for Metropolis, but just sit back and let the computer run a few million iterations, they can figure it out for you. So that's good from a practical point of view, but as I hinted, we can say, wait, is this valid theoretically, right? And I'm a theory guy, so will it still converge? And it seems to work well in practice, but will it necessarily converge to pi? And as I already said, the whole reason MCMC works, why? Because we have Markov chain theory that's 100 years old that tells us about convergence of Markov chains. Now we're tweaking it as we go. We're not running a Markov chain. And we're not, this destroys the Markov property. And does that make any difference? Well, let me go back one more time to the simulation. And what I'm going to do, I'm going to keep doing this. Remember, we have this adaptive version that does plus or minus 1, but then it accepts plus or minus 1, 2, and so on. But let me change the target. So I'm going to change, let's see, to a different target. And this one is, it's still another, okay, I'll stop it. It'll be too distracting while I say, sorry, here, let me get rid of the black bars while I say there's a new target, which is still on 6 points. It's still points that add up to 1. And, it's still going to be our new target. I just tweaked it a little bit so that 5 of these bars, 1, 3, 4, 5, and 6, are all exactly the same and just a tiny bit less than 0.2. And then 2, you can maybe just barely see there's a tiny little bit of blue there because pi of 2 is very, very small, but still they add up to 1. So it's still just another potential target. And then I can start running the Metropolis algorithm. And I guess I can put back the empirical bars. So it's going to run it as it goes. And, but again, it's doing the adaptive version. So it's tweaking this plus or minus 1, 2, 3, whatever, based on whether it accepts or rejects. And it still kind of looks okay. Now, you might say you're a little nervous because it's hard to jump over 2, but if the radius of proposal is more than 1, then you'll jump over it, no problem. Let me run this faster because I don't have too much time left and I want to make a point. So it's running around now, and finally it'll get over to 1. And sometimes it'll go to 1, and sometimes it'll go back, and it seems sort of okay. But eventually it will get stuck in a certain trap. And possible some of you can see the trap coming, but the point is, you say, okay, well, it's going to go back and forth, no problem. And this radius of proposal will increase and decrease, and the black bars will adjust. But eventually, okay, oh no, it almost happened. Almost got stuck. By the way, it's running randomly each time in case that wasn't clear. I didn't plan this, but eventually, and if I have to, I'll make it run faster. It'll get stuck in a trap, and maybe you can kind of sort of see what the trap is. So getting to 1 is okay because it could have a big proposal, and then getting back's okay. But you say, well, what if it gets to 1 and then it rejects a few times? That's where things might get more interesting. And am I gonna maybe have to speed this up? Give it one more second. Usually it happens by now. Okay, I'm gonna speed this up. Just okay, I know what's happened. All right, let me speed it up. So I'll go to warp speed for a little while. It's still not happening. Ottawa's weird. Okay, eventually what's gonna happen, I can force it if I have to, but is it gonna happen to go to 1? And then it's going to happen to reject a few times, and then it'll just be doing plus or minus 1 from 1. It'll take a while. Wow, I'm going to go to hyperwarp speed. Okay, there we go. It's gradually slowed down. Now let me get it going slower again. So what happened is eventually, and I did have to rush it, it took over 300 iterations, but it happened to jump to 1, which it does from time to time, no big deal. But then it happened to reject a few times. And remember, the adaptive rule was if you reject a few times, you do a smaller radius. And now suddenly it finds itself at 1, but just doing the plus or minus 1 version. And now, well, whenever it proposes to 0, it always rejects. When it proposes to 2, it almost always rejects because we had just such a small amount of blue here. So we say, gee, it's not doing too good, and it's going to get stuck there, right? Now, at first you might say, well, okay, it'll get stuck for a while, so it means the black bar at 1 will get pretty big. But that's fair, because then eventually it'll get out, and then maybe these black bars will get bigger too. But not quite, because if it's over here, then it has some chance of accepting and then getting a bigger jump, and it might jump back, no problem. But if it gets to this trap, it's very hard to get out of it. And the smaller we make pi of 2, the harder it is. So even if I run it really fast now, it's running nice and fast, but going nowhere, right? And it's not just that it'll take a long time for the black bars to converge to the blue bars. The black bars will not converge to the blue bars. And in fact, the smaller I make this pi of 2, the more in the limit, this black bar this one will get close to 1, and these will get close to 0. So it's actually converging to the wrong thing. So when I learned this, it kind of scared me, because I thought, I want to talk about how to adapt Markov chains or Metropolis algorithms, but if you adapt them, you can not just make it worse, you can totally converge to the wrong thing.
Do you wait for burning time and then adapt, or you start from?
Well, it's a good question. Yeah, there's different, that's an implementation issue. And usually we would do some initial runs to get some samples before we have anything worth adapting to. So that's a good question. Yeah, usually we would do some running and then some adapting once we have some samples. Yeah. Okay, so anyway, so it does matter. And so what we want is, from a theory point of view, we want to show that under some conditions, maybe the adaptive version will still converge to the right thing. So, and by the way, one thing you can do in practice, and probably if you're just practically going to run adaptive MCMC on a real problem, probably what you really want to do is just run adaptation for a while to try to get what seems like a pretty good Markov chain, and then just stop adapting and run regular MCMC, because we all know that that works okay. But especially if you're more on the theory side, you might say, yeah, but how do you know when to stop adapting, right? So maybe you want to keep on adapting as you go. So this theory is about what if you keep on adapting? And we have a couple of theorems, and I'll just say a little bit about this. So this is joint with Gareth Roberts, by the way, a lot of this is. And we say, well, suppose you have two conditions. One of them is called diminishing adaptation, and it means you adapt less as time goes on. And the formal condition is, look at, this is comparing, this is P sub gamma n plus 1. So that's the Markov chain transitions you're using at time n plus 1 in your adaptation, compared to P sub gamma n, or the Markov chain transitions you're using at gamma n. So how different is it, your transition probabilities at time n plus 1 compared to time n? And this is actually what's called the total variation distance. It's just a way of measuring the distance of those proposals. And it's saying that better go to 0 as n goes to infinity. So the amount that you change from time n to n plus 1 in your tweaking better go to 0. You can still do an infinite amount of tweaking. You know, the sum of the changes can still be infinite, but just the amount of change from n to n plus 1 better shrink down to 0. So that's okay. The second one is a technical condition called containment, and it says the time cessationarity remain bounded. So there's a formal definition that's a little bit of a mess, but it says let mx gamma be how long you would have to run that choice of a Markov chain starting from that initial point x in order to get within epsilon of stationarity. So that's some number, you know, we have to run it 500, 1,000, whatever. And then if you run your adaptation, you're tweaking the point that you're at, and you're also tweaking the choice of Markov chain. But suppose it's true that no matter how much tweaking you do, at least in probability, the time to return stays bounded. So it's really just saying that the tweak, as you tweak as you go, it stays bounded in probability. So it doesn't sort of scoot off to infinity. And you know, A can be made to hold, B is a technical, it avoids this escape to infinity. So one way I think of it is, you could imagine you do adaptation where you say, well, I've got a bad Markov chain, but that's okay, I'll run it and get some samples. But then you get some bad samples, and then you get an even worse Markov chain, and it gets worse, and then you get even worse samples, and then you get a worse Markov chain and worse samples. You can sort of escape off to doing something infinitely bad. And that's what containment controls. It seems to hold in practice, and we have proven it under some conditions, depending on the tail behavior of pi. But it's sort of this awkward proposal, so awkward condition. And I must admit, for a few years, I sort of had this basic theory, and I would tell adaptive people, you know, tell applied MCMC people, you know, you should try this adaptation. We think it'll work really well, but you have to be careful with the theory, or you could converge to the wrong thing. But we have good theory to say, okay, I'm going to do it. I'll make sure I have diminishing adaptation, no problem. And how do I make sure I have containment? I say, yeah, well, you can't really check that. So you just have to hope that it's okay. And it usually will be okay. But I was obviously not very happy with that. So, and as an aside, we did prove that validity under various different MCMC schemes. So we were working away at it, but we had this nagging feeling that you can't really, you know, easily verify this containment. And then later we came up with a way to ensure it. It's a little bit clumsy, but it's a way to sort of fill that gap. And let me just quickly say that before I end. So the idea is we say, well, let's treat this adaptation as being a sort of adversary. That is to say, usually we think adaptation is trying to help us do a better Markov chain, right? But in order to prove that it can't do this escape off to infinity, let's imagine there's an adversary who's tweaking the Markov chain to try to mess us up, right? And we say, what rules could we put on this adversary so that he can't mess us up too bad? And we all know that small changes to a Markov chain can have a big effect later. So for example, this is if you imagine a simple random walk where you say you have a 51% probability of going right and a 49% probability of going left. Well, in the long run, you're going to go to the right, right? Or if you have a 51% probability this way and 49 that way, in the long run, you're going to go that way. So little change in the probabilities could make a big difference. So how can we control that? So we said, well, and this is actually my colleague, Radu Krayu, some of you know, suggested this. And he said, let's assume, first of all, to keep it simple, that these Markov chains never move more than some big distance d. So that could be a big distance, it's not a big deal, but not that they can in one step go off to infinity. So we sort of have some control. And then let's also assume that all the adaptation and all the tweaking is done in some big rectangle K. So some rectangle K, and we do whatever tweaking and adapting we want here. But if you get outside K, then you just do regular Markov chain, okay? Regular MCMC, let's say. And again, it can't jump more than D. So he said, well, would that be enough to ensure containment? And I said, yeah, that should be enough, no problem, right? But I was wrong. So here's what I learned from that. I thought, is that enough to ensure this tightness condition that you can't escape off to infinity? And it turns out the answer is no. And there's various counterexamples. Let me just say this quickly. I don't want to take too much more time, but here's an example where you say that we have a state space where the x values are 1 and a half and a third and a quarter and a fifth and so on. So these are sort of 1 over n. And then for each one of these, there's an infinite stack in y. So it's an infinite stack of positive integers. And each one of these is running a simple Metropolis algorithm, but with higher and higher means. So if you're at 1, you run a Metropolis algorithm, but you stay pretty small. If you're at 2, you might get a little bigger. If you're at third, you might get a little bigger, and so on. When you get up to a 10 somewhere, you could get pretty big. And we say, let's let that K be the red dots at the bottom. And they say that, you know what? Suppose I'm an adversary and I want to mess this up. I can mess it up because what I can do is when you come down to K, I can keep sending you further to the left here so that you're going to actually go higher and higher up the ladder. And anyway, I won't spend too much time on the details, but the point is we realize that even if you only move one step at one distance at a time, and the adversary can only mess things up way at the bottom, still the adversary can set things up so that you're going to be more and more likely to go higher and higher. So that wasn't sufficient. But then what we did come up with is that we said if in addition to A1 and A2, you have some continuity conditions. So if the transitions or just the proposal kernels are continuous, and that fixed kernel outside is just bounded above and below on compact regions, then that's sufficient. So what we said is that this awkward containment condition that, it usually holds in practice, but we didn't really know how to prove it. And it was awkward for telling applied people to use Markov chains. We said, you know what, if you satisfy these sort of continuity conditions and these boundedness conditions, then it is satisfied. So at that point, I felt like, hey, adaptive MCMC can be used for anyone if you're willing to verify these conditions and you're guaranteed that you'll converge the right thing and you can try to make adaptive rules that make it work faster. So any rules that will help you and that satisfy these 4 conditions, you can just stick them in. Okay. So let me just summarize. I've gone on a little too long. So, I'm someone on the theory side, and it's always a bit awkward trying to convince applied statisticians that theory can be useful to them as they run MCMC, but I believe it can be. So the basic thing is it shows why we can use MCMC and why it does converge, and that goes back to the 1950s. But then also we have these diffusion limits, and these diffusion limits give us things like optimal acceptance rates, things like 0.234, and also things about the slowdown factor and how it's fastest if your proposals are proportional to the target covariance. So it gives you guidance to use. But on the other hand, we can't make that much use of it because it needs these things that we don't know. But if we use these adaptive versions, they can learn as they go. And we say, hey, these adaptive versions, they could mess things up. We have those examples. But if you have diminishing adaptation and containment, then you'll be okay. And then we say, okay, containment is kind of awkward, but if you take this adversarial approach, then there's 4 sort of checkable conditions. They're a little bit clunky, but they're pretty checkable in terms of continuity and boundedness. And then they guarantee containment too. So hopefully that's enough for it to try on these various examples. So I'll leave it there and take questions. But again, thank you very much for your attention. Thanks to Kenzie for having me, and thanks to the University of Ottawa for your kind hospitality. So thank you very much.
In the classical MCMC, you have diffusion limit. Do you have any type of Strass-Excellence limit for the adaptive?
Well, that's a good question. I mean, it's hard to control, right? Because first of all, it depends what your adaptive rules are. And then, yeah, it's a good question. I guess because I mean, there's with adaptive, like there's a few things going on at once, right? Because on the one hand, there's the Markov chain trying to converge to stationarity and so on, but then there's also tweaking the rules as you go. And even just what sometimes people ask is easier than your question, but it's already too hard for me, is just how do you control the relative convergence? That is, how much adaptation do you have to do before you get a Markov chain, which is going to converge better and so on, like, so those things. But then in terms of diffusion, yeah, it's a good question. I guess it would have to be a very clear and regular adaptive rule, right? It couldn't be anything too weird, or it just wouldn't have a limit. But it was something like, for example, the adaptive Metropolis, we usually do it where we do the new proposal based on the empirical covariance matrix. So I guess in principle, it could be that the covariance matrices are, well, of course, in the limit, we hope they're going to converge to the true covariance matrices, and then the Markov chain will converge to the optimal one. So that could be a limit. But as far as the diffusion along the way, like what it does, yeah, it seems like a good question. You should figure that out, and you should let me know. Yeah, it'd be complicated though, because there's so many different aspects going on. That's a good question.
Any question? In the adaptive model, let's say we use the proposal distribution as normal. This SN that you're estimating from the previous data, does it asymptotically converge to actual variance of the population?
So
It's large.
SN, you're talking about the empirical. Yeah, the sample, right. Yeah, so I guess, I mean, no matter what proposal covariance you're using, in principle, if you run it long enough, then you should get samples which are converging to the true samples from pi. And if the samples are converging to the samples of pi, then their empirical covariance should also converge to the empirical covariance, to the covariance of pi. So is that your question? So in principle, the covariance of your samples should converge to the covariance of pi. Is that your question, or?
I was, because we want to eventually draw a sample from the actual population,
right,
which is affected by the sample variance, right? That you're using for adaptation. If the sample variance converges to the actual population variance.
Yeah.
So adaptive will work, right?
Yeah. So I mean, again, to say it formally, you'd have to say what the adaptive rule is, because you can make a crazy adaptive rule that messes it up. But if it's a reasonable adaptive rule, like the adaptive Metropolis rule, then it should be that as you run it longer and longer, that so a few things should happen, right? The adaptive scheme should converge to an optimal MCMC, but also the samples from MCMC should converge to samples from pi, and then that means that the empirical covariance from the samples should converge to the true covariance of pi. So all those things should happen. I just want to be a little careful, because I guess if you did a crazy adaptive rule like the ones that I showed the counterexample, then it would fail. But if you're doing, I guess if you're doing adaptive rules which still follow these conditions, so it will converge, then everything should converge. So in principle it should, but how quickly it does is also a question of question. Yeah. Thank you.
So it's first of all, it's nice to see you using the applets, because I've actually used those in class. It's kind of fun to see them.
There you go.
At least those are things inspired by them.
Excellent.
But so in terms of adaptation, so there have of course been a lot of flavor twists on Metropolis tastings, like Hamiltonian, Monte Carlo,
right,
all sorts of things like this. It seems like the same adaptation rules that you're talking about shouldn't break if you change to Hamiltonian Monte Carlo.
Yeah, pretty much. I mean, the good thing about it is, our general theory is really just, if you satisfy a few conditions, then you can adapt pretty much, any MCMC any way you want, right? As long as you satisfy a few conditions. So then oftentimes people tell me, okay, well, I've got this problem here and I've got this MCMC. How should I adapt it? Like, well, I don't know. All I can say is if you satisfy a few conditions, then it'll be asymptotically valid. But with things like Hamiltonian MCMC, there's things like how many steps you should do until you do your accept reject, and you can do adaptive versions of those things, right? And you can say, well, if for example, if you're usually rejecting, maybe you're doing too many steps or whatever, and in principle, you can adapt the number of steps, you can adapt the step size, you can adapt all the different ingredients to go into Hamiltonian Monte Carlo, and say as long as you're a little bit careful on the conditions, it'll be asymptotically valid. But then the question is, what are the good ways to adapt it that will help your problem while still maintaining the conditions? And in some sense, I always tell people that they're in a better position than I am. Like if you're using it on an applied problem, then maybe you have a sense of, the problem is how it's always getting stuck here because it's never doing that. But if we put in an adaptive rule that says, hey, if you reject this 3 times in a row, then you should add an extra step here. Like anything like that, that's a sensible rule that satisfies the conditions. In principle, you can do. And I say, yeah, please do it. And please tell me how it goes and so on. But as far as, exactly what should be done, like that's largely not settled. But I would say, yeah, in principle, like there's nothing about, even though the example I gave were just the original Metropolis, but it's really, the theorems are just about any collection of Markov chains which have the right stationary distribution and any tweaks of them. So in principle, all those things can happen. And yeah, if you got some thoughts that way, I'd love to talk more. So if there's any Zoom questions, maybe not.
I haven't seen any.
Okay.
Okay, thank you for a nice talk. I guess there's no other questions, right? Thank you very much again.
Okay, thank you. Merci. See, one says there's something in the chat. I don't know if it really is, but one came up with the one in the chat.
Oh, now there is something.
Is it a question?
Thank you very much for your very informative talk. Are there specific types of target distributions where adaptive methods consistently outperform traditional MCMC?
I'm trying to answer. Are we still live? Or I could say that's a great question, and I'd say in a lot of these examples, what it is that adaptive MCMC, if it's done well, will converge to an optimal one. So it's not so much that it outperforms any MCMC, but like with Metropolis, it'll help you find the good Metropolis instead of the bad one. So that's usually the way it works, is that adaptive helps you to find the best versions of the traditional MCMC.